it says calculate delta H for that. One of the things is these are all gas phase. I don't know if I said that in the problem. But what you're doing is breaking things into the different atoms, and somewhere on the quiz there's probably a table of bond energies. Since you're going to use a table of bond energies, I'll use the table I usually use. In fact, the table in the textbook. So I guess I should write them all in here now.
Bless you.
And usually in organic chemistry, you don't bother putting the hydrogens in, you just draw bonds. And there are other ways of doing this. We'll talk about that when we get to the organic chemistry part of it. But here I put it in like this when I wrote the problem so you can see the different bonds. The only bond I didn't put in, and this one I did put in oxygen. Remember the other day in lecture I said, I would expect you to know that oxygen is a double bonded molecule. Because that was one of the, when we were talking about bonding with N1A, that's always the thing you talk about. What else do you know? Single bond, H2. What about nitrogen?
Double bond.
Triple bond.
Oh, triple.
Ah, I did that last year. You're supposed to remember that? Yeah. I told you last year, you have to remember everything I say until you're finished with Chem 1A and 1B, because I expect you to remember it until the end of the semester. After you take the final, I don't care what you do with it. So probably, if you take organic chemistry, Dr. Jones will still expect you to remember some ionization. Okay? Now here again, when I lectured the other day, I said that sometimes I give you the structure for CO2, but sometimes I don't. If I write CO2 like this, you have to remember that it's two double bonds. We did all of this with the electron dot structures last semester. And then notice here I wrote water, and that's because water is the first thing we ever talk about almost in chemistry. And by now you should definitely know for water it's what? Hydrogen oxygen bonds. And you should even know that water has a bent structure, right? Okay. Then, what's next? Well, it said, find the bond energy for that C double bond O, and it gave you what? The delta H for the reaction. Okay. And I went through two different ways of doing this. First of all, you do need to balance the equation. I think it's balanced correctly. 1, 2, 3 carbons, 3 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 8 hydrogens. So here I have 3 times 2 is 6, plus 4 is 10. Here I have 1, that leaves 9, so the coefficient is 9/2 in front of the oxygen. And as I said, the way it was written, it gave you delta H, and it wanted you to find one of the bond energies. That means when you went to the table of bond energies that I put on the quiz, you couldn't find this bond energy. When I give you quizzes, I mentioned this, I give you some data tables, but I leave out selected pieces of information, either because I want you to calculate it, or sometimes in the case of the enthalpies of formation for elements, or the free energies of formation for elements, you're supposed to remember that for elements it's 0. So there's lots of times I give you tables of data where there are big blank spaces in it, because I want to give you those numbers, I want you to calculate something. So here obviously I left that number out of the table of bond energies. But I had to put in the other bond energies, otherwise you couldn't do the problem. Maybe that's what your question was, how could we do the problem? Because you found the problem but didn't find the data table that went with it. Okay.
which if you don't have the data, then it's gonna be tough. But I always give out a data table, and sometimes I put on a quiz. Don't forget to look at the data table, or I put on the top of the page. Data is on a separate page, because sometimes people come in late and they don't know there's a data page, that table, that separate page with the data that came with the quiz. So I was looking for my bond energy table again. Because I don't think he has it in the back of the book. But here it is. So anyhow, there it is. What you would have found on the table would have been things like C-H, and it says C-H 414. You would have found C-C, C-C 34, and that's single bonds. 347. You would have found C-O down there, 360. And you would have found H-O. And by the way, I probably put in a lot of other ones that you don't really need to use, mostly because some of these I just copy out of the thing and paste them in, whatever way. So there are some extra ones that you might not need. You just have to look at the molecule. Now, at the end of the semester, after we do organic chemistry, I wouldn't necessarily give you the structure for this thing, because one of the things we'll concentrate on when we do organic chemistry is drawing structures and names that go with them. We're not going to do the things that they do in the real organic course, where they concentrate on reaction mechanisms and pathways, because this is just a little survey, and probably the most important thing to get you started is how these things go together. So coming back to this thing, H-O is in here somewhere, 464. And C double bond O is what I asked you for. I would have to put this in the table. And you looked over here, it's 498. And the other one, H-O, I already put in there. So I have all the bond energies, so I'm done with that. Okay. Now, I want you to see it when you get sick. Here he doesn't do it too much, but on the slides, when it tells you how to set these problems up. On the slides, he always says, and the slides don't work out too well because of the formatting. He always wants to put it in this form, the delta H. And I guess he just use delta H for this, we could put a 0 there, because I said we do this all in gas phases. I'll leave it as delta H. And I said the easiest way, and that's what he's saying here, you're doing delta H for bond breaking, and you're adding delta H for bond formation. Now when you form bonds, that's an exothermic process, so these are negative numbers. When you break bonds, you always have to add energy. It's an endothermic process. Delta H is positive. And I said that's the easiest way to put it in, because you're looking at the balanced equation, you put it in, but he wants to do products minus reactants. And if you want to do products minus reactants, what you have to do is make believe that these are all negative numbers in the table. Okay? And,
Dr. Dan?
yes.
I think it's reactants minus products.
Okay, what he does the next thing here, since these are, let's see, bond formation, yeah, these are on the product side, so he puts the minus sign out here. And he doesn't, yeah, he does do reactants minus products, but on the slide, he tries to do products minus reactants. So you see a contradiction between the slide set that goes with the textbook and what he put in the textbook. But what he's trying to do is be consistent, and here, and usually, you don't want to confuse students by saying reactants minus products, because when you have a delta, what does it mean? The final state minus the initial, so delta would always mean products, that's the final state minus the reactants. And so when I set this table up like this and said you just put minus numbers in, it's so it would follow that same format. Oh, I got that page there already. Because that's what you always think of for the delta. It means it's a state property, so it's always the final state minus the initial. So if you wanted to do it like this, you make all of these negative. Effectively what it turns, if it doesn't turn this around, it looks like that. If you just use the bond energies as they appear in the table, then you'd use this formula and leave them as positive numbers. The important thing is you get the same sign for the answer either way. And I like the business where you just think about breaking bonds and forming bonds, because that makes sense. That's the most logical way, at least as far as I'm concerned, of doing it. So, finally, problem. And I'm going to do it the logic way. I'm going to break all these bonds. So if I'm breaking bonds, I'm going to write it as a positive number. And I have 1, 2, 3, 4, 5, 6, 7, C-H. And sometimes I write it down for myself. In fact, that's how I do it when I set up the solution so that I can see what everybody did. And so I say 7 times plus 4, 1, 4. I have 1, 2 carbons. So I go 2 times 7. I have C-O, so I have 1 times, I look up C-O.
Dennis,
Yes.
make sure, for some of the examples in the books, they showed like sometimes the bonds would break and some of them don't. Like, for this one, do they all break, or?
Yeah, because what you're doing is going from this reactants, this set of reactants, to that set of products. And the imaginary thing you do is you're breaking all the reactants down into atoms. So you're forming all these atoms, then the atoms recombine in a new structure.
Would you ever have a situation where only like some of them break, like maybe you lose an OH and then something else comes in?
Well, that might be the mechanism how it goes, but the theory here, and notice if you look at some of the solutions in the book, sometimes we'll have HO, in fact, let me write that. 1 times O or O-H, whichever way you want to write it, will be 1 times 464. Now on the other side here, you have 8, because there's 4 molecules with 2 hydrogens, 8, and when the book solves it, in his solutions, he doesn't put these down, he doesn't put this one down, he just puts what over here? 7, and everybody said, how come he got 7? Because he had 1 on the reactant side, and 8 on the product side, so there's a net of 7. So in his solutions, he does the net thing. And I said, you can do it that way, but it's a lot easier just to write down all the bonds you're breaking and all the bonds you're forming, and then add them all together. Okay. So mechanistically, this may not be what happens, but this first of all, the joke I make when we do organic chemistry, I say, what's the product that you get when you oxidize something? And one of the products is always, if you're careless and set your reaction on fire, you're always gonna get CO2 and water vapor, or possibly carbon monoxide and water vapor. You do that in the organic lab, and they kick you off because you're a hazard to everybody. And in the organic lab, Dr. Jones doesn't keep open flames. Remember I said I keep the ether up at the stockroom window because I don't want it out there where you have the laboratory flame. If you have 10 drops in your test tube, you set it on fire, I don't care, it's gonna go out before you notice it. But if I put my whole bottle out there and you set it on fire, it'll sit there and burn, and everybody say, wow, look at that. Okay. So that's what they do in organic chemistry too. They work with little heating mantles and things rather than having an open flame, because most organic compounds catch fire. You catch fire. Every so often you read something about somebody bursting into flames, probably because they're drinking alcohol and they breathe out instead of breathe. I don't know what they do. But anyhow,
What?
your body's burning is what it boils down to. Okay, so coming back to this, because you're breaking down all these carbon, and this is a really drastic thing. So mentally, you could probably say you probably do disrupt all these bonds and form new carbon-oxygen bonds. Other reactions you do where you're trying to convert this to an aldehyde or a organic acid, you use oxidizing agents that are not as strong as this. You don't set it on fire. And now you just, making an aldehyde, you sort of make a double bond here and get rid of the hydrogen. Okay? So then you're not breaking up the whole molecule. You can still analyze the energy change by going through this though.
Okay.
So this is going to work whether the thing is completely disrupted or whether it's not, because if you're making the aldehyde, these bonds are all going to stay the same, so they're going to be on that side now. So let's see, I got all the bonds for this thing. I have 9/2 moles, and it's O double bond O. And for O double bond 498. And what people always do is put an equal sign in here. It's not equal. You're adding bonds that you're breaking, and you're adding the bonds that you form to get the overall energy change. Okay. So what you say is, now you add all of these up. Then over here you have H8HO. So you say, and since you're forming the bonds, energy is given off, then you have minus 464, and you have 3 times 2, 6, 3 times 2, 6. That's what you're solving for. So what it says is in the problem, delta H is minus 19.04. 19.04 kilojoules. And by the way, in the bond energy table, these are always kilojoules per mole of bonds, because it takes a lot of energy to break bonds. Okay? So it's minus 94. You add all of these things up, it's 6 times X in the formula. It's 8 times minus 464. These are all going to be positive. And now you solve for X. Okay? I'm too lazy to get my calculator out. But you can do that, right? Yes?
If you got, if you change the 464 to negative, shouldn't you put negative for X?
Guess what it's going to come out when you do this? It's going to come out negative when you solve that equation. It's going to come out as a negative number when you solve it. Because you have the, is it minus 1904, or did it say, yeah. You have the negative number here, you're bringing all of these positive numbers over here, it makes it even more negative, you're bringing that negative number over here, makes it positive, but it's still gonna be essentially negative, then you're gonna divide by 6 and you're gonna get a negative number. And usually, and again, if you wrote that as a positive number, I wouldn't worry about it because the table gives these numbers always as positive, and the student has to recognize what type of sign you're putting in for the process. We're converting CO2 into carbon atoms and oxygen atoms, then we put whatever number we got in here as a positive number. But since it's on the product side here, it'll automatically come out to be negative. Okay? So that takes care of that. Any other questions?